Okay, so I think on Thursday we talked about synapses and how they work. So you get a vesicular release that releases neurotransmitter, and so the action potential triggers the release through calcium. And then there's a certain number of neurotransmitters or vesicles that are released at each synapse. So we can change the strength of the synapse. So what can we change about a synapse to increase or decrease the strength? The further the distance, the less neurotransmitter to make it from one side to the other. It turns out I think clefts are usually pretty static. Yeah, but that's a good idea. What else? The number of vesicles, we can change the number of vesicles that are released. So that's called a presynaptic mechanism, by increasing the number of vesicles. Changing the number of receptors, so that's a postsynaptic change. So those are, the other most obvious one is that you could change the size of the vesicles. But it turns out that that's the other thing that's relatively fixed. The synaptic distance and the size of the vesicles are fairly well constrained. And the two major things are the number of vesicles that you release and the number of neurotransmitter receptors you have. And so here is an example. This is done by fattened cats. It's a very famous experiment. You can see the size of the postsynaptic amplitude given across a whole bunch of stimuli. And so you can see here are the number of ones that were at 0.4 millivolts in size, the number of synaptic responses that were 0.8 and 0.17. And you can see these troughs that are in here around 0.6, right? And this is because this is one vesicle being released as you stimulate the presynaptic cell. This is 2, this is 3, this is 4, this is 5. So you actually can almost, by looking at the size of the postsynaptic response, identify how many synaptic vesicles were released. And it turns out the number of synaptic vesicles released for a single action potential at a single synapse is really pretty small. There's usually only 1 or 2 or 3 synapses. Most probabilistically are single vesicular releases. There's also just spontaneous, even without an action potential, sometimes it released a vesicle. And those are called sponts or spontaneous synapse, and often they will look at the rate of sponts to determine whether changes that happen presynaptically. So if you change something like the probability of release, you would expect to see the rate of spontaneous event releases to change, and if that can tell you whether there's a presynaptic or postsynaptic change. So we could change the vesicle size. That doesn't really happen much. We could change the number of vesicles. By changing the number of release sites. We can change the probability of synaptic release at its site, making it more likely for a given amount of calcium to release a vesicle. We could change the density, the number of synapses. So Desi, is it Desi that discovered the silent synapse? So one of the faculty in neuroscience department actually discovered that there was lots of synapses or at least in cell culture that were silent. They didn't actually have receptors on them. But if you stimulate it a lot, suddenly it would add in receptors into these, and suddenly it becomes an active synapse. So you have literally an anatomical connection there, but it is not functional. And by stimulating, you actually cause the functionality. So that was discovered here at the University of Minnesota. Or no, by somebody at the University of Minnesota. You probably discovered it before coming here. Okay. And we can also change things like the rate of opening of channels and the length of a receptor being on. So by changing these alphas and betas slightly, we can change there's alphas and betas for the neuroreceptors too. An example of this is a really nice review paper by Zucker in 2002. If you stimulate, and this is measuring an EPSC, so you see a synaptic input come in, a current coming in, and then you stimulate immediately afterwards here's 20 milliseconds. There's an increase of calcium sitting in that presynaptic synapse. Right? So the first action potential comes in, a little bit of calcium comes in to release. Second action potential comes in, it actually summates the calcium, and there's a dramatic increase in the probability of the synaptic release. And so that second synaptic coming in second action potential coming in can often release almost twice as much neurotransmitter. So here's examples as a function of the timing between the first and second synaptic input, the strength, so one being the size of the first one, and the second one being stimulated within 100 milliseconds can often be 2.5 times the size of the first input. So this is a principle which is really important, that if you want to send a signal through to the postsynaptic neuron, sending a bunch of action potentials in rapid sequence, now this is what we call a burst of action potentials, really dramatically increases the probability of an event on the postsynaptic side. You dump much, much more neurotransmitter. So here's an example of we're stimulating very, very quickly, and we look at the size of the synaptic inputs postsynaptically, and you see, so here is very, maybe stimulating once a second, so we get an average, we scale that to 1. We start stimulating very quickly. We get a rapid increase in the size of the EPSPs, and then we start stimulating once a second. It immediately drops, comes up a little bit, and then slowly drops over time. So there are many different things going on. The first one is there's a rapid increase in that calcium, which causes facilitation. Okay? That saturates pretty quickly. And then you actually have longer-term things happening, which is called post-tetanic potentiation. And those actually are caused by changes in either you take the channels and you phosphorylate the channels and it changes their opening and closing, or you actually add in more receptors, and that slowly builds up over time and then slowly degrades over time. And then there's also what's called depression, which will slowly, and this happens more often when you're looking at very rare events, will slowly weaken connections. Because you got to have some kind of, you can't just strengthen connections all the time. You have to weaken them over time, and depression's always there as well. So if you stimulate kind of infrequently depression, that you will actually weaken synapses between. And there are also rapid, if you stimulate really rapidly, you might get some facilitation initially, but then you might actually deplete. So there are primary glutamate stores, so you have those vesicles that are docked and ready to go. And then when you released all of those, it takes a little time for the vesicles that are sitting up sort of inside the synapse to actually migrate down and then dock. It's called docking, and then be released. And so you have a little pause between the first volley of synaptic release and starting to come in with the bringing in the recruits and releasing those. And that you will see a drop in synaptic release for a little while that happens. So we talked about Hebbian plasticity already. So the sayings that we use to remember Hebbian's plasticity is that cells that fire together wire together. Okay, so when they fire, they will stay wired together. And if the other one is if they're out of sync, they lose their link. So the guys that are not firing together, if they're synapsing onto the same guy, will drop that connection. And then the other is correlation is heard and validated. This sort of is the maintenance of connections. And it's by correlations you see in firing rates between the inputs and outputs. So here's an example of synaptic depression. Here is the size. We just stimulate once, and we measure the size of the EPSP. So the first stimulus is fairly large. We immediately stimulate shortly afterwards, and you actually see it decreased. If we're putting in a Poisson train, so you actually, the intervals between inputs is varying randomly. The lines are the actual experiments, and the dots here are based upon a model. And that model shows that after each, let's say time 0 is just after the neuron has received its first input, and this is the time of the second input. So just after the first input, you actually double the probability of a synaptic release, and then you drop it back down to 1 with some kind of time constant. And then there's also depression, which you drop it simultaneously down to 0.4, and then it relaxes back up to 1. And then there's a slow depression, which drops just a little bit to like 0.975. Yeah, and then it has a very slow time constant. And so then you take all three of these numbers, the facilitation, depression, fast depression, and slow depression, you multiply those three numbers together, and that gives you whatever the predicted value is from the last time intervals. Does that make sense? I feel like I've done a terrible job describing that. So we stimulate here, okay, and then we have a facilitation, we have a fast depression, depression fast, and you have a depression slow, okay, and each one of these, they're starting off at 1, and we add some kind of value to it. So this is facilitation. So this automatically bumps up to 2 right here, and then it's decaying away with some kind of time constant, the facilitation. And this one is coming up and comes back to 1, and we have some depression fast, and we have some depression slow, which comes as a smaller and a very slow. And now when we come in, let's say the second input comes in. We'll put in a second input here. This causes this to go up and then start to come back down here. This one was here. It drops it back down. And this one here is very slow. It drops it by this. And then we look to see what these three values are. We take how much strength we add to the synapse is dependent on F times dF times ds at each of these times. And then if you have another one comes in here, you would see these are probably coming back to 1. This one would drop, but this one you'd see the slow depression is building up here, and this one. So by adding each of those, this tells you how much synaptic release at each time of those by multiplying all three of those numbers together. And they're just simply decaying away. So long-term potentiation is like a more permanent change in the strength of the synapse. So these are all very short-term changes that happen, but long-term potentiation happens, you have to have lots of inputs, and they sort of sum up and change the synaptic strength over a very long period of time, up to years, apparently. And so there's many ways we can strengthen, and one of them is by adding in more receptors. This is called amplification. Another is you could actually trigger more synapses to connect between cell A and cell B. That's called synaptic doubling. You could split them, or you could add in new ones, or you can awaken old ones. Or we could actually take things that are inside the cell to modulate the receptors. So here's an example. The size of the synaptic input, or the EPSP, we see when we're stimulating about once every second. You know, it's average of, we just set that to 100%, right? And now we give it a 50 hertz train. It stimulates very fast. You see accumulation of calcium inside the cell, and you see immediately afterwards the synaptic strength is increased, but it drops. Okay, so that's the facilitation there. But then you see, for a very long time, you see a 25% increase in the synaptic strength. If you stimulate it at 200 hertz, you actually see facilitation again. It drops down. This is probably the depression following. And then you actually see a recovery, and you see a facilitation, almost a 200% increase in the strength. And if you start stimulating at very slow rates, like 1.5 hertz, that actually causes a weakening of the synapse. And you can see it drops from 100% down to, wow, these are dropping a lot, down to like 20%. It was very hard to actually find a protocol that reliably induced depression. So there was a lot of debate about whether depression worked. So here's sort of the general hypothesis. You have a synaptic input. Sodium comes in as well as calcium. And we know calcium inside the cell is very, very low. There's lots of calcium chelators, keeps it very low. But when it comes in through the synapse, through the sodium channels, it causes a little bump. And if it's a big bump, it actually causes a bunch of protein kinases, which actually start phosphorylating proteins, and then that actually phosphorylates the receptors and increases the amount of the amount of current that they let through. Whereas if it's a little bit of calcium that comes in, it actually does the exact opposite. It actually activates protein phosphatases, which actually decrease the amount of phosphorylation of the receptors, and it decreases the amount of current that goes through. So there's sort of a general rule, which is called the BCM rule after, I think it's Bernstein, Cooper, Monroe. I forget the first guy's name. But the idea is if you have, here's the amount of facilitation that you would see, and this is the amount of calcium that you would see. So if you have just a little bit of, if you have 0 calcium, there's no real effect. If you bring in a little bit of calcium, you induce LTD. If you bring in a lot of calcium, it induces LTP. So it's kind of a weird model. It's a very superficial model, but you see LTD, small amounts of calcium, LTP with lots of calcium. So what is this? Why does this happen? One hypothesis is that you're putting in these receptors. So here are these presynaptic guys are stimulated. This guy has a lot of receptors in here. When those vesicles come in, they cause calcium to come in. That actually causes all of these signals from calcium to signal to move receptors up into the synapse. And so it actually moves those receptors up and makes these guys more sensitive to the next synaptic input. So that's called amplification, because it's adding in more AMPA or NMDA receptors. Both are different glutamate receptors. I think that should have been covered on Thursday, the difference between AMPA and NMDA, right? Okay, so this is a very famous paper by B and Poo, don't laugh. And what they said is, hey, normally what they do is they stimulate really fast the presynaptic cell, and then you see an increase in connection. But they said, let's not stimulate really fast. Let's stimulate the presynaptic cell, and let's stimulate the postsynaptic cell. And we'll change the timing between whether they're stimulating the presynaptic cell before the postsynaptic cell or after the postsynaptic cell. And they discovered that it's really, really important that the synapses are looking for causal relationships, that a presynaptic cell has to fire before the postsynaptic cell if you want to increase that strength. So it means that that presynaptic cell somehow was influencing that postsynaptic cell to fire. Okay? We want to strengthen that. And so here you can see this is the postsynaptic cell firing just after the presynaptic cell. You get a 100% increase in the synaptic strength. But if the presynaptic cell fires just after the postsynaptic cell, it means it didn't really help cause that to fire, and so it actually weakens it. It drops it by maybe 20% in the amplitude. And if the stimulus is really very, very late or very, very early, it really doesn't seem to affect the spike times at all. So this is what's called a spike time dependent plasticity rule, meaning that depending on whether the presynaptic cell, and you have to repeat this like 100 times, stimulating pre-post, pre-post, pre-post. Do that 100 times, and then you'll see this increase in the synaptic strength. Or post, pre-post, pre-post, pre, and you'll see a 20% drop in the strength. This is really important in understanding plasticity in the brain. And so I'm actually working on a model inspired by the conference where people were saying, hey, let's stimulate the trigeminal nerve, and they're seeing that the trigeminal nerve actually decreases somebody's chances of having epilepsy, but you only even have to stimulate at night, and it decreases their probability of having seizures during the day. Well, why does stimulating do that? Well, one is that it's causing all these neurons to fire, and when just after they fire, they send out all these synaptic inputs, but because everybody's already fired, they can't fire again. And so they actually, now what we're seeing is all these synaptic inputs are coming just after they have fired, and that weakens the connections. And so by stimulating the trigeminal nerve, causing a bunch of people to fire to an external input, you actually weaken all the connections within the network. So we're making a quick little model to demonstrate that. And you can say you knew me before I got the Nobel Prize. Okay, so here's long-term depression. This is the neurons fire out of sync, lose their link. The idea is that you're losing AMPA receptors. And whether you lose synapses or not, or make them silent, it's not really known. So here's just the opposite. You receive a synaptic input. Just a little bit of calcium actually. Wait. Oh, this is sort of the correlated ideas that these two guys, if they fire together with another guy, it will actually cause these guys will strengthen because they all fired together, but it will cause the guys on the other side who did not fire with it to weaken. So this guy will remove receptors because these neurons did not fire at the same time these guys did.